For over half a century, silicon has been the bedrock of our digital world. Its semiconductor properties allowed us to miniaturize transistors, fueling an unprecedented technological boom. From the smartphones in our pockets to the most powerful supercomputers, silicon microchips have been the engines of progress. However, as we pack ever more components onto a single chip, the inherent physical limitations of silicon are becoming undeniable. Heat dissipation, power leakage, and quantum effects are now serious barriers, signaling that the era of relentless, easy growth for silicon might be reaching its inevitable ceiling. Gordon Moore's famous observation, that the number of transistors on a microchip doubles roughly every 2 years, has guided the semiconductor industry for decades. This exponential growth has delivered incredible gains in computational power. Yet, recent years have seen a noticeable slowdown. The costs of designing and manufacturing ever smaller silicon transistors are skyrocketing, while the performance benefits are becoming less dramatic. We're now contending with fundamental physics, electrons behaving unpredictably at atomic scales, making it increasingly difficult to sustain the historic pace of innovation without entirely new materials. Enter graphene, a material that could potentially redefine the future of electronics. Discovered in 2004, graphene is essentially a single layer of carbon atoms arranged in a hexagonal lattice, a honeycomb-like structure. Despite being just one atom thick, it is astonishingly strong, 200 times stronger than steel by weight. But its true revolutionary potential lies in its electronic properties. Graphene boasts unparalleled electrical and thermal conductivity, allowing electrons to zip through it at incredible speeds with minimal resistance. This makes it an ideal candidate to pick up where silicon begins to falter. The comparison between silicon and graphene highlights the stark performance divide that could reshape our technology landscape. Silicon is a semiconductor, meaning its conductivity can be switched on and off, which is crucial for transistors. However, it's a relatively poor conductor of heat and electricity compared to metals. Graphene, on the other hand, is a nearly perfect conductor. Electrons in graphene travel without scattering, leading to vastly superior mobility. This translates directly into faster processing speeds and significantly lower power consumption, addressing silicon's core limitations head-on, particularly in high-frequency applications where heat is a major issue. When it comes to raw processing power, graphene's potential is nothing short of revolutionary. Imagine transistors that operate at terahertz frequencies, far beyond the gigahertz limits of today's silicon chips. Graphene's electron mobility is hundreds of times greater than silicon, allowing for computations at speeds previously considered theoretical. This could lead to a quantum leap in computing performance, powering everything from advanced AI to real-time, complex simulations. The development of graphene-based transistors, though still in early stages, holds the promise of breaking through the gigahertz wall and ushering in an era of unprecedented computational speed and efficiency. Graphene's impact extends far beyond just faster processors. Its remarkable flexibility, coupled with its transparency and conductivity, opens up entirely new categories of electronic devices. Think of paper-thin, rollable displays for our phones and televisions, or smart clothing embedded with sensors that monitor vital signs seamlessly. Wearable tech could become truly invisible and unobtrusive. Graphene's ability to conduct electricity while remaining transparent also makes it ideal for advanced touchscreens and solar cells, potentially making every window a power generator or interactive interface. The possibilities for a more integrated and adaptable electronic world are vast. The implications of graphene also resonate deeply within the energy sector and for environmental sustainability. Graphene can dramatically enhance energy storage solutions, leading to supercapacitors that charge in seconds and batteries that last significantly longer while being lighter and more efficient. Its high surface area and conductivity make it exceptional for catalysts, potentially improving fuel cells and reducing industrial emissions. Furthermore, graphene membranes show incredible promise for highly efficient water filtration and desalination, offering a sustainable solution to global water scarcity. This versatile material could drive significant advancements in green technology. Despite its immense promise, graphene's journey from laboratory marvel to widespread commercial application is not without its hurdles. One of the primary challenges is scaling up its production to industrial levels while maintaining high quality and low cost. Producing perfectly uniform, large-area graphene sheets remains a complex and expensive endeavor. Furthermore, integrating graphene into existing semiconductor manufacturing processes requires significant innovation and investment. Developing graphene-based components that are stable and reliable over long periods also demands extensive research. These are not trivial problems, but the global scientific community is actively working to overcome them. The potential of graphene has spurred significant global investment and research momentum. Governments, universities, and private corporations worldwide are pouring resources into graphene R&D, anticipating its transformative impact across numerous industries. Dedicated research centers, like the Graphene flagship in Europe, are spearheading collaborative efforts to accelerate its commercialization. While a complete replacement of silicon is unlikely in the short term, graphene is increasingly seen as a crucial complementary material, augmenting and eventually surpassing silicon in specific, high-performance applications. The race to unlock graphene's full capabilities is well underway, promising exciting breakthroughs in the coming years. In conclusion, while silicon has served us faithfully for decades, its inherent physical limitations are pushing us towards a new frontier. Graphene, with its extraordinary electrical, thermal, and mechanical properties, stands as the most promising successor and complement to silicon. From vastly faster processors and flexible electronics to revolutionary energy solutions and advanced sensors, graphene holds the key to a future where technology is faster, more efficient, and seamlessly integrated into our lives. The transition will be gradual and complex, but the scientific and industrial momentum behind graphene suggests that the silicon era is indeed preparing to yield to the dawn of a new, graphene-powered age. The question isn't if, but when and how profoundly this material will change our world.